So hello everyone, my name is Sarah Latif and today I will be presenting the content for week 5. So this is like part of the professional machine learning certification study group which has been presented and animated so far by Zahra, Rosa, Majid, Patti, and for these 2 upcoming weeks, myself. So we will quickly remind where we are in our journey, go through some exam guide review, some sample questions review as well. I will be taking your questions and answers. I will be taking your questions throughout the whole presentation, and then we'll preview actions for next week. So where are we exactly in our journey? So we're actually on week 5. So if you have been keeping up with the material that has been available so far and studying everything, then congratulations, you are 2 weeks away from, taking the exam. So we will be actually reviewing, we will be reviewing actually 2 things today, which are the ML monitoring, pipeline automation, orchestration, and the monitoring, optimization, and maintenance. In brief, MLOps, using some of the tools that might have actually already presented so far, and then the TFX, TensorFlow Extended. So normally in an ML process, you usually ingest the data, clean it, perform some feature engineering, build the model, and then deploy it. But when you deploy the model, usually as new data comes in, the model needs to be updated, or perhaps you have added some new feature, or perhaps you want to update the task. So in any kind of way, you will still need to update the process. And if you update the process in a manual way, where you don't have some kind of dynamic way of actually doing it every time you add a component or something new, it's going to be very time consuming and impractical. That's why it is better to automate most of what you can do, if possible, of course. So we will check out things like how we can train the model, integrated as continuous training trigger, perform automatic continuous evaluation, and of course we will try to see how we can use TensorFlow extended to construct end-to-end ML pipelines and get rid of all the headaches of doing these things ourselves. So what exactly is MLOps, or machine learning operations? So actually this term has come from the DevOps, which is developer operations. So actually it's the same principle where you have an application and you want to deploy it to production. And as you know, sometimes with applications we always kind of there are some bugs. The framework we're working with has been updated, so we need to update mostly everything, or we need to check out security dependencies. So there are a lot of things happening that are dynamic. So if we don't kind of find a way to update our simultaneously and then in real time, well, it's going to be very difficult for us to keep up to date with what is happening out there. So before, what was done was that we had developers alone working alone, and then we have the operations people working alone. So there was no actual interaction between the 2 teams. And later on they figured out that it was better to mix, to integrate both people at the same time, so they can collaborate, update, and one can actually understand the struggles of the other team, and they can update and figure out how to solve problems in synchronization, not each one alone in a corner. So that's kind of what is happening in machine learning. So right now, the data scientists or machine learning engineers are expected to understand how their model is going to be deployed, and of course take responsibility on how it's going to be deployed. So it's not going to be the responsibility of the operations people anymore. So we better put some practices in place to make this a bit less stressful, right? So how do we gain confidence in this, in this MLOps process of pushing our models to production and making sure, obviously, that everything works and that it keeps working after all? We don't want it to break in halfway. So small steps, small improvements, small iterations, which we call continuous integration. So for efficiency, continuously incorporate new small changes, and we need to verify that they still work, right? So that's what continuous integration is all about. You introduce something new, perhaps you add some new feature, you add some new class, then try to see, update, try to see how the environment is reacting to it, and then you can keep making changes. So don't get out all the way. Don't develop and then later on push to production and be surprised it doesn't work. All right. So apart from the continuous integration part, we have what we call the continuous deployment. So well, we have made obviously the changes. We need to deploy them into production so that our user can access them. So how do we deal with this? So we need to automate the deployment and the validation of our models to make sure that they work and they continue working. So now with every small improvement that we have made in continuous integration, we can immediately on the fly deploy and start to get value from that work. So before it was not uncommon to deploy to production 3 to 4 times per year. Obviously, changes happens simultaneously. So we need a way to if we push a new change, it can be reflected directly. Now, continuous training. So this is actually what is special about the ML ops in comparison with the DevOps thing. So in machine learning, obviously, we train models. So we need to talk about continuous training because if you update your model, there's going to be something called data drift, and that means changes in the model. So, for example, there might be more variations that you didn't have previously in your previous data. So, you will need to account for that, and accounting for that means that the model needs to be retrained. So, models are obviously, like I said, susceptible to feature drift, concept drift, a lot of drifts, and continuous monitoring of the performance. And when it drops below a threshold, trigger retraining. I mean, that's what we should be taking into consideration. But now, in order to do these things, all of the three aspects, we no longer have enough with our ML framework. The typical ones. So, tools for building components. So, as I said before, data scientists before had to only worry about developing the model, training it, but now we have to worry about MLOps too. So, and that means monitoring, serving, configuration, process management, you name it. And obviously, all of it is related to the data. So, luckily, we have a tool that that we will be spending some time explaining, and that's TFX, or what is called TensorFlow Extended. And it's actually a framework developed by the TensorFlow team to build MLOps pipelines, including all of the components. So before we only look at the ML code, but this time we'll be looking at the trainer component, and we will be needing all of the gray boxes surrounding the training component. So here we are showing the TFS components that are the implementation of the functional boxes on the previous slide. So we have, for example, data analysis and validation, which is implemented by TensorFlow validation, data transformation and feature engineering implemented by through the TensorFlow transform, the trainer, hyperparameter, tuning are done by Keras. Then the model evaluation and validation is done with TensorFlow model analysis. Meanwhile, for serving of the model is implemented using TF serving. So here are the specific TFX components that implement the functionality. So for data ingestion, we have what we call the example generation. It actually just means that if you have, for example, usually your data is going to be in various forms. So you need to prepare it into a specific format. For example, if you're going to work with tabular data, it needs to be, set in some kind of format, like rows, for example, and columns. And you, of course, you have to update also the format of your columns and all of that. So for TensorFlow data validation, we have something called statistic generation. You would, after all, sometimes you are interested to know about the mean of the data, the standard deviation, and all of these kind of things. Max value, min value. So we kind of figure out if there are any outliers, and just understand the data. Then we have something called the schema generation. You can think of this as the SQL part, when you're, for example, trying to define a structured database format, for example, you would, set specific, we can call them columns if you want to call them that. So, for example, name, you would say like defining the name, defining, for example, the profession of a person, some kind of social number. So these kind of things are called schema generation. And then we have what we call the example generator in the data validation. So for the transform, obviously, we have the transform functions. For estimator or Keras model, we have the trainer. For TensorFlow model analysis, we have the evaluator. And then for validation outcomes, we have the parser. As for TensorFlow serving, we have the model server or TF serving. And here we show the components with their logical dependencies. So for example, with our training generation that, for example, you have after you have, you introduce your data, you will be, setting them into a specific format, then you will be drawing the statistics, and you would have, for example, an example validator, a schema generator, transforming your data so you can feed it to the trainer, evaluate on it, push it for more validation, and then, of course, feed it to the infrastructure. So for the data analysis and validation, so we'll be actually looking into the data analysis and validation component. We will be looking at all of them, only at two components. And this data analysis validation is actually implemented by the TensorFlow data validation functionality. So let's take this example where, for example, you have day one data, and like the if we follow the logic that we saw before, so the next thing that we will be doing is trying to first the example generation component, where we will be setting the like reformatting our data, for this case into tabular form. We will be generating the statistics. So as you can see here, we have day one statistics. And as you can see, they provide us things like count, missing values, the mean, standard deviation, and all of the things that you would, for example, do if you were using, for example, pandas, like data frame.info or something like that. So after computing the statistics, which are actually important not just for us to figure out what is happening, but later on when we will talk about the drift, we'll understand why exactly they are really needed. So we will try to infer the schema, try to understand the logic, so we can format our all data into this format. So for example, here we have feature name fair as type float, and for example, company as type string, of course, company name. So after we generate this schema, we will perform schema validation. So what do we mean? So that means that so we have day one, we already inferred the schema, so we already have a proposition of a schema, and then let's say we introduce a new like a new data. That means day two. So if we introduce day two, and like if what we proposed is similar to what is found in day two, then we're safe, everything is good, everything is working. It's because we have the same let's say column names, the same types of the data, so we won't have a problem. But in case we do, TFX will take care of that. The schema validation will help us take care of that. That's why actually TFX is so powerful. Now, there is another things we talked about a lot before, which is the data drift. So the data drifts can also be represented in here, where they call it training serving skew detection. So for example, if we let's say for example day one data is very different from day two data. Let's say for example we thought that feature X was always above 40, for example, but then when we introduced it day two, we figured out that feature X is actually can actually be zero or something else. So if there is something like this, this kind of huge difference, which we call the data drift, then we would have, if we have already trained the model, deployed it, then we would have to retrain on this new data, taking into account this difference, so we can recalculate the statistics, so that if we come with another example similar to day two, we will be able to you know take it into account, and the prediction of the model might be better. And this thing as well, GFX take care of it. It takes care of like if new data has come in, it has different statistics, then it will try and retrain the model. Now let's talk about the data transformation implemented using TensorFlow transform. So usually when before feeding your data to the machine learning models, you kind of do need to transform it. So you might need to scale it, bucket it. If it's NLP, textual data, you might want to do some backup verse, create some n-grams, perform some feature crosses, or just apply some kind of other transform. Now, let's talk again about the training service queue. So, training service queue in general is a difference between the system during the training phase and the system in production, right? I think we got that right now. So, it can be due to feature drift that we can detect using the TensorFlow data validation, as we have seen. And it can also be due to different implementation in production. So compared to what we were doing in training, so during, for example, training, we were reading the features from cloud storage, right? Or something. And then we transformed them. And during serving, well, it doesn't work out anymore. It's because in serving, for example, we got the data using an HTTP request. So the format might have changed or something might have happened. So we need to adapt. So for example, the new HTTP request will have to be pre-processed so that it can look the same as the cloud storage so our model can work. Well, with TensorFlow Extended, we don't really need to do that because we can implement a function that is called processing function that will help us do this kind of transformation. And of course, this ensures that same operations that we apply in the training environment are going to be applied in the production environment. And this is how TensorFlow Transform helps us with the prevention of this training serving queue. So there are still more components that unfortunately we won't cover, we won't address today. But I wanted to show you one slide related to serving because apparently it pops up in the exam. So as you can see, so we have, for example, the training process in the left side, and then we have something called the deployment process. So apparently the thing that they still don't cover when they go over the shared material that you have, all the quick labs and all of that. So the thing that they cover is this is this deployment thing. So I'm not sure if you know this or not, but usually when you have huge models and you want, for example, to deploy them on an edge device, that could mean an Android application, to an iOS Android, or or some kind of multi-platform framework. Well, obviously you can't deploy the original model as it is because the device won't be able to handle it. So what we usually do is that there are some kind of ways we try to reduce the weight of the model and that the size of the models. And these kind of techniques are, for example, pruning. So that means getting rid of some layers that don't help in the prediction or inference part, or for example performing quantization, some kind of way to compress and reduce the size. And these kind of things can be done using the TensorFlow Lite components. So the TensorFlow Lite components and some other components can actually like help you train the model using uh, the normal TensorFlow core you're used to or Keras, and then you feed it to a certain library. I mean, the TensorFlow write library using the export function, which will reduce using one of the techniques I talked about, pruning or quantization, and then make it easier for you to deploy the same model on any edge device, and that means Arduino, Android, or something like that. Do we have any questions? Okay, now let's look at some sample questions. So let's say we need to build an object detection model for a small startup company to identify if and where the company's logo appears in an image. So we were given a large repository of images, some with logos and some without, of course, of the startup. So these images are not yet labeled. So we need to label these pictures and then train and deploy the model. So what should we do? So the options are: use Google Cloud's data labeling service to label the data, then use AutoML object detection to train and deploy the model. That looks like an interesting way of doing things, right? And that might be doable. Now let's see option B. So we can use Vision API to detect and identify logos in pictures and use it as a label. Then use the AI platform to build and train a convolutional neural network. So a Vision API, and let's say, for example, our startup is new, very small. We, there is a very low chance that the Vision API has been trained on any of our logos. So there will be lots of struggle and lots of errors from the Vision API if we use it. So we might want to scratch that. So C, create two folders, one where the logo appears and one where it doesn't. Then manually place images in each folder. Use AI platform to build and train a convolutional neural network. So that means doing the job ourselves, right? And that might take more time than needed. If we're going to do something like that, obviously it's going to be expensive as well. We better go for the Google Cloud data labeling service to make it faster and save on resources. So option D is actually very similar to option C, apart that they are proposing to actually train an object detection model. And obviously, if you ever have tried to label data for object detection model, it takes a lot of time and it's very tedious, and you need lots of hands, hands to help you label, and you need lots of data for your model to converge. So that leaves us with option A as our, option to go with. That means use Google Cloud's data labeling service to label our data and use AutoML's object detection to train and deploy the model. That will be faster and perhaps will save us some resources. So the second question is, so we work for a gaming company that develops and manages a popular massively multiplayer online game. And then the game's environment is open-ended, so large of number of positions and moves can be taken by a player. Our team has developed an ML model with TensorFlow that predicts the next move of each player. That's nice. Now, edge deployment is not possible, so we can't deploy this on a mobile device. But what they want is that they obviously low latency serving is required. So they want our model to take less time when it's making its predictions. I mean, as much less time as much less time as possible. So this is like one of the things where you want to use the TA flight option. So how should we configure the deployment? So they suggest we use a cloud TPU to optimize model training speed. If we use the cloud TPU, it's going to take a lot of time for us to have the inference in a very short time. Because the thing about cloud TPU is that it actually does speed up training, but it does not really reduce the time it needs for it to load all its libraries and all the things we need for it to work. So we might want to scratch that. Now let's check out for B. So we can use a deep learning virtual machine on compute engine with an NVIDIA GPU. Oh, that's nice. So practically we, instead of using any CPUs or anything like that, we can just deploy the model on the GPU and have its inference returned back to us. That might save us some time, especially if we can use several GPUs in parallel. Now, for the option C, use AI platform prediction with a high CPU machine to type to get a patch prediction for the players. So, CPU, and especially for you in some kind of very high end deep learning model, they don't really go well with each other. It's going to take forever to get, just one one player's movements will take a lot of time to infer or to predict. We might want to scratch that too. So for D, we can use AI platform prediction with a high memory machine type to get a batch prediction for the players. Well, using a high memory machine is very similar to using a high CPU machine. So unless we're using, some kind of very highly advanced sets of servers, or using a GPU, then it's better we go with the GPU option. That's it. Do you have some questions for me? So let me just finish with previewing our actions for next week. So for next week, it will be a week full of MLOps. That means that you will have to go through MLOps material. And for me, I will be helping present some, I will be quickly going over what was done in the previous weeks and then explore some other questions with you from the exam. Please remember to join our Slack group through this link. And if you need any help, you can either contact us or get in touch with the GDG community.dev or support. And that's it. Thank you very much. And if you have any questions, please, you can either leave them here or leave them in Slack.